Welcome back, physics folks. This is the last treatment of this chapter, and it's going to be a quick once-over on the four fundamental forces. So the first two are ones that we deal with every day, that we're familiar with. And the second two are ones that are critical and explain why matter acts the way it does, but we don't experience directly on a daily basis. So, number one is gravity. All right. This can be defined a lot of ways, but for us, good enough is mutual attraction between all masses. Every mass has a great gravitational attraction to every other mass. It is the weakest force. Okay, when you think about it, you can bend down and pick up a watermelon, even though the entire mass of the earth is pulling down on that watermelon. Okay, so it's not a strong force, but because of all the mass in the universe, it obviously has some really important properties. So, the second one, which we also experience directly, is the electromagnetic force. Historically, electricity and magnetism were thought of as two separate entities. They were discovered differently and thought of as differently until finally, I think it was Maxwell who put the thing together and realized that they're interrelated, and a changing electric field, that's worth writing. A changing electric field produces a magnetic field, and a changing magnetic field produces an electric field. Okay, it's got to be changing. Now, this force plays a part in more things than you may realize. It plays a role in these, among other forces and experiences we have. Elasticity, adhesion, friction, contact forces, and many more. Okay, this is a result of the atomic structure, the unique atomic structure of atoms, ions, and their interactions. All right, so these two are, we know these. We experience these. Numbers 3 and 4 are nuclear. 3 is one that explains a seeming contradiction when you first learn about the anatomy of an atom. Right? So this is the strong nuclear force. And a few key points to this one is it is only in the nuclei of atoms. It is the strongest by far of the four fundamental forces. It acts at very short distances. We're talking fractions of an atomic diameter. Okay, acts at very short distances. Its power drops off dramatically with distance. And it keeps protons of the nucleus together. All right, at short distances, it's much stronger than the electromagnetic force. So you have the electromagnetic force where positives and negatives are attracted to each other, and the same charges, positives are opposed to each other, repulsed by each other. Negatives are repulsed by each other. All right. So the strong nuclear force is attractive at very short distances between protons, and against that is the electromagnetic force that's repulsive between the two same charged particles, between the two protons. So it's basically an attractive force between protons. Now, if you think about the anatomy of an atom, and we think of a bunch of protons, all those plus signs are protons, and you got some neutrons in between there. Okay. Now, these protons that are very close together are going to have a very strong nuclear force, and the electromagnetic repulsion between them is going to be very small by comparison. But if you take these two, all right, here, the strong magnetic force, the ones in blue here, the strong nuclear force is much smaller and getting closer to the magnitude of the repulsive force that's pushing those positive charges apart. So you could see that as a nucleus gets bigger, as the atomic number of an atom gets bigger, it's going to become less stable, because the positive charges that are distant from each other, that are toward the outside radius of this nucleus, the strong force between them is going to drop off dramatically, and the electromagnetic force is going to become stronger. So you could see that would pose like an upper limit to the size of an atom, and as you approach that upper limit, it would definitely affect the stability of that atomic nucleus. And then, lastly, we have the weak nuclear force. And where the strong nuclear force is in every nucleus, every place you have a nucleus. This force basically occurs in some reactions between elementary particles. It's a more specialized reaction, and we're not going to deal with it in any detail here. So it controls nuclear decay, which I'm sure you're familiar with. And it controls nuclear decay, controls how a neutron can change to a proton plus an electron. Plus an electron. Okay, and the weak here is weak relative to the electromagnetic force. Okay, obviously weak compared to the strong nuclear force. Okay, just one little aside, and then we'll be done with this. But in today's society, if you don't know about nuclear fusion, you should have at least a basic concept of this. This is what the sun does. And in the context of what we were just talking about, the electromagnetic force and the strong nuclear force, basic nuclear fusion is taking two hydrogen atoms and creating a helium atom. Okay, so a hydrogen is basically one proton plus one electron, and it can have neutrons. There are different forms of hydrogen. So the trick with fusion is when these two hydrogen atoms become helium, fuse together to become helium, there's a tremendous release of energy. Okay, so when H plus H become helium, there is a tremendous release of energy. The problem with nuclear fusion, the problem is it takes a huge amount of energy to overcome that electromagnetic repulsion, so the H's get close enough so the strong nuclear force can take over. Can dominate. Okay, and that on Earth, trying to do fusion has been the sticking point. It's taken more energy to make the helium than to get out of the helium. And in the sun, this happens because stars are massive. In fact, you can't have a star unless it's supermassive, because it's that gravity from being supermassive that forces this fusion in the core of the star, so that you can create these elements. And it's not just helium plus helium. This is the easiest case. Stars do this. They just keep going up the chain. That's where all our elements up to iron are made. And iron, for energetic reasons, the reaction takes more energy than it gives, and they peter out around there. And the elements above that have to be made in supernovas, where you have extraordinary forces working. So that's a wrap up of chapter 6, and thanks for joining me, and we will see you in class real soon. All right, bye-bye.